This drill bit is spinning at high speed, tearing through a solid block of metal and ejecting heavy chips. If you're framing a workbench, you just need a hole big enough for a bolt. But if you're a machinist pressing a high-speed bearing into an engine block, that same approach will destroy the workpiece. There is a common assumption that making a hole is a one-step operation. You take a 10mm drill bit, drive it in, and expect a 10mm hole on the other side. Relying solely on a twist drill bit for a high-tolerance job is a reliable way to ensure your parts fail to fit together during assembly. This flowchart illustrates the 10mm dilemma. The top path uses a single drill to hit the 10mm mark, which terminates in a fail icon because the dimensions are unreliable. To pass inspection, you follow the bottom path: drill, then bore, and finally ream. Achieving a perfectly precise diameter requires a sequence where bulk material removal gradually gives way to strict geometric control. Penetrating solid metal requires immense initial force. When you apply that much pressure to tear through steel, you lose control over the exact path of the tool. Using the wrong machining operation results in sloppy alignment, wasted material, and workpieces that have to be scrapped. Every project involves a trade-off. You have to decide if the speed of a single operation is worth the risk, or if your tolerance requirements justify the time and tooling investment of a multi-step workflow. Knowing when to stop at drilling, when to step up to boring, and when to finish with reaming protects both your schedule and your budget. Drilling is your first step. It is used exclusively for penetrating solid material where no hole existed before. This typically involves a twist drill bit, which uses two cutting edges to dig into the metal. At this stage, you are prioritizing rapid material displacement over the retention of a specific shape. Because drill bits are long and slightly flexible, they tend to wander as they dig deeper. This means the resulting hole is rarely perfectly straight. Additionally, that aggressive cutting action leaves the interior walls with a rough, irregular surface finish. Due to vibration and bit flex, the final diameter is unpredictable. It usually ends up slightly oversized or even oval-shaped. You should treat drilling strictly as an excavation phase. It's great for clearing out bulk metal, but it cannot deliver high-end precision on its own. This leads to boring. This process can only be performed if a hole already exists in your material. Instead of the dual flutes of a drill, you use a single-point boring bar that cuts along the inside edge of the workpiece. This matrix shows trade-offs. Drilling has high material removal, but low accuracy. Boring takes that existing hole and enlarges it. The matrix updates for boring with moderate ratings. Its critical function is correcting wandering alignment, shaving walls until perfectly straight. To achieve this straightness, you have to use slower feed rates. This produces a surface finish that is better than a drill's, but still only moderate in quality. Boring acts as the alignment bridge. Without this step to fix the geometry, you cannot achieve true precision in the final stage. Reaming is the final, high-precision finishing process in the sequence. A reamer doesn't dig bulk metal. It shaves microscopic material off walls. Returning to our matrix, reaming provides high accuracy and smooth finish, but low material removal, hitting an exact diameter with a mirror surface. However, a reamer is designed to follow the existing path of the hole. Because the tool isn't rigid enough to cut a new angle, it cannot fix a channel that was drilled crooked. Reaming is for final sizing and finish, not alignment. It will fail to provide a precise result if the boring step was skipped. Let's look at how this works in practice. You're making a machine part that requires an exact 10mm hole with perfect alignment. First, a twist drill clears bulk metal, leaving a rough 9.5mm hole. Next, a boring bar widens it to 9.8mm, shaving the walls perfectly vertical. Finally, the reamer shaves the last 0.2mm, polishing the exact 10mm hole for a perfect fit. Producing a high-tolerance hole depends on the specific progression through multiple specialized tools. If you're building a simple frame or using standard clearance bolts, drilling alone is the correct, efficient choice. But for engine cylinders, aerospace components, or bearing press fits, precision work requires the full time and cost investment of all three steps. One final rule: don't buy a reamer to fix a crooked hole. If your alignment is wrong, a boring bar is the only tool that can correct it. Match your machining sequence to the tolerance your part requires, and you'll stop fighting your tools.